Fellow physics students, this is Dr. Brenzi. This is lesson 5.1.5 for advanced physics. We're going to be revisiting some terms that we learned in our first lesson in this unit, and I'm going to introduce some additional terms. And the reason I'm waiting until now is I didn't want to overwhelm you with too many terms at the very beginning. But now that you have a better grasp of circular motion, I wanted to come and reintroduce some of these terms that you could have used maybe with what we've done so far, but we're going to have to learn some of these terms for what we're going to do in the second half of this unit. So the first thing that I want to revisit is the idea of period, and if you remember, a period is the amount of time it takes to complete just one lap. Now, frequency is the number of laps that you can complete in a certain amount of time. Excuse me. So you can think of starting an hourglass and saying, okay, this hourglass is going to run for a minute, and then I'm going to count the number of laps that I can run in 1 minute. So, period, we already know this, but I'm just going to put this up here. And if you want to refresh your memory, you can go ahead and write this down in your notes. So let's remember that this is the Greek letter tau. But the new term that I want to introduce to you is the word frequency. And we usually use the Greek letter nu, N-U, for frequency. So nu is the number of revolutions that can be completed in a unit of time. Probably the most common way that you've encountered frequency is when you look at the dash in your instrument panel of your car, you'll notice something that says RPM, which stands for revolutions per minute. So that's the number of revolutions that your engine is completing in a minute. So that is a measure of frequency. Usually, though, with frequency, we want revolutions per second instead of revolutions per minute. So there's a relationship also between frequency and period. That is, if you go 2 revolutions per minute, your time to take 1 revolution is going to be half a second. So if you can do, in 1 second, you can do 2 revolutions, 1, 2. So your frequency is 2 revolutions per second. Then the amount of time it takes for you to do 1 revolution is obviously half of that. So it would take you 1/2 of a second to do 1 revolution, so your period would be half a second. So you can use either of these formulas. You can say frequency equals 1 over period, or you can say period equals 1 divided by frequency. Either formula will work. So let me give you a couple of really quick examples. So let's say a car engine revolves with a frequency of 2,500 RPM, which stands for revolutions per minute. What is the engine's period? So if I were to use the formula tau equals 1 over nu, I would say that tau equals 1 over 2,500. And if, let's see, 1 over 25, that's 0.04. So this is 0.0004. Wow, that's a lot of zeros. Or if we were using scientific notation, we would write this as 4 times 10 to the negative 4 times 10 to the negative 1, 2, 3, 4. 4 times 10 to the negative 4 seconds. Oh no, that's not seconds, that is minutes. Why is that in minutes? Because my frequency is in terms of revolutions per minute. So if I'm being asked to provide this car's period in seconds, then I would have to do a unit conversion. So we have 60 seconds in 1 minute. And if I were to multiply this number times 60, I would get 2.4 times 10 to the negative 2 seconds. At least I hope I'm doing my mental math correctly. I believe I am. So I would have 2.4 times 10 to the negative 2 seconds, or if I wanted to write that as a decimal instead of scientific notation, I would say 2.4, and then I move 2 decimal spots over to the left because that's what negative 2 tells me to do. So 1, 2. So instead of 2.4, I have 0.024 seconds. Okay. So that would be my period in seconds. So let's say we have a wind turbine that revolves one full circle every 1.2 seconds. So its period tau is equal to 1.2 seconds, because that's the amount of time it takes to go a full circle. What is its frequency? Well, frequency nu equals 1 over tau. So that's equal to 1 divided by 1.2. And that's going to give me, let's see, a number that's somewhere close to 0.88. That one I'll have to kind of look up, but anyway, if you were to punch this into your calculator, you'd definitely know what it is. And what are the units? We would say this is revolutions per second. Okay. So that would be my frequency. Okay, what I want you to do next is I want you to go ahead and check your work, or check your understanding, excuse me, by doing this practice problem. Pause the video, and when you unpause it, we'll quickly compare results and see what you come up with. Okay, I'm going to assume that you paused the video. So let's see here. We have a drive shaft that rotates once every 2.5 milliseconds. So 1 millisecond. Well, actually, let me back up. I should say my period tau is equal to 2.5 milliseconds. And there are 1 second in every 1,000 milliseconds. So there are 1,000 milliseconds in 1 second. So if I were to do that unit conversion right there, I would get 2.5 times 10 to the negative 3 seconds. And if you take nu equals 1 divided by tau, you're going to get 1 divided by 2.5 times 10 to the negative 3rd. And let's see, 1 divided by 2.5, that's about, this is 2/5. So 1 divided by 2.5 is 2/5. And 2/5 I know is 0.4. So I have 0.4 times 10 to the negative. Well, actually, there's negative thirds in the denominator, so 1 over 10 to the negative third is the same as 10 to the positive 3. And if you're not sure about that, test that in your calculator. It turns out to be 4 times 10 to the 2 revolutions per second. Or if we just want a regular number instead of scientific notation, that would be 400 revolutions per second. That's what I got. So now I'm doing all this with mental math, so if I happen to have done a calculation wrong, please let me know. But this would be the process that you would use to figure out the frequency. Now, you've encountered this next concept in math class before, but I understand from Ms. Shipley that you're not so strong at it, so it's a good idea to go over this again. Radians are a very important concept in physics, and they're going to be a very important concept later on in our unit, so we have to get a really good understanding of what a radian is. So if you are on a circle and you start here, and you decide to yourself, okay, I know the radius of this circle is this much, and I want to walk this distance along the circumference of the circle. So you count out as you're going along the circle how far you've walked, and then when you would stop right here once you get an entire radius worth of length along the circumference of the circle. Now your angle has changed by what we would call 1 radian. So a definition of a radian is the angle that is subtended by an arc length equal to the circle's radius. So if I say, oh, I know my radius is this long, and I'm going to walk along that around the circumference, then the angle that I've created here from between where I started and where I finished is 1 radian. Now, why are radians useful? Well, radians are useful because you can quickly convert between how far you've walked along this circle in meters, and you can quickly convert that to an angle. Now, if you're trying to measure this angle in degrees, you would have to say, okay, how many degrees are in a full circle, and how much would I walk around to get in a full circle? Well, it becomes harder. So, with radians, that calculation becomes rather simple. Now, in a full circle, you know that the circumference, c, equals 2 pi times the radius. So if you to go around in a full circle and come back to where you started, you have walked 2 times pi times the radius of the circle. So if there are 2 pi times r meters in an entire circle of circumference, then there are going to be 2 pi radians in the full circle. So if you walked a full circle, you have gone 2 pi radians. If you go half of a circle, you have gone pi radians. If you go a quarter of a circle around, you have gone pi divided by 2 radians. Okay. So it's a quick way to convert from angle to length around the circumference. So let's apply that to a circle or circular motion. We already know what linear speed is. It's the amount of, that's the rate at which you cover distance over a particular time. So let's say if you walk a total of 6 meters around the circumference of the circle, and you do it in 2 seconds, then you would say that your linear speed, v, is equal to 6 divided by 2, which equals 3 meters per second. Okay. Your angular speed, and we're going to assume that the radius of this circle is also 3 meters. So if the radius of this circle is 3 meters, and if you've walked 3 meters around the circumference, you have gone an angular distance of 1 meter, or 1 radian, excuse me. So you have gone 1 radian in angle, and then if you were to take another second, so 2 seconds total, you would walk 2 radians. So you could calculate the rate of change in angle over time, and the change in angle, delta theta, is going to be equal to 2 radians, and over the change in time, 2 seconds. So we would say that this person's angular speed is 1 radian per second. Okay. So linear speed, if you review your notes from the very first lesson in this unit, 5.1.1, we know that it's the rate at which a point changes its linear position along the circumference of the circle, and we put this in units of meters per second. We also got a good understanding that if a point is closer to the center of the circle, it is going to have a lower linear speed than a point that is farther out on that same circle. So this point has to go faster to complete an entire loop or an entire revolution than this one right here. This one doesn't have as far to go. It has to go that in the same amount of time, so it will not need to go as fast. So speed, or linear speed, gets larger with a larger radius. Now angular speed is different. First of all, in physics, we use the Greek letter omega. You may have heard that letter before. Omega is the rate at which a point changes its angle over time. Now these same 2 points, even though they have a different linear speed, they're still going to change their angle by the same amount over the same amount of time. So what that means is that angular speed does not depend on how far the point is away from the center. So these 2 points on the same circle are going to have the same angular speed, but they're not going to have the same linear speed. If you want to calculate angular speed, you would say the angular speed is 2 pi, because that's the number of radians in a full circle. So a full circle has 2 pi radians, and then you would divide that by tau, which is the amount of time that it would take to complete a full circle. So angular speed equals 2 pi divided by tau. It looks a lot like linear speed. The only difference is linear speed has an extra factor of r in it. Well, that's an ugly looking r, so let me change that, and let me make it a small r, just like the, oh no, it's, changed my mind, back to big R. And then we're going to divide that by tau. So the only difference is that there's an extra factor of tau here. Do you now notice that 2 pi divided by tau, that is equal to omega, so I could replace those 3 things with omega, and I come up with this formula that omega times r is equal to linear velocity. So there is a relationship between angular velocity and linear velocity. Finally, I want to show you centripetal acceleration, because you know that centripetal acceleration is equal to v squared over r. Now, if we take our formula that says v equals omega times r, And if we replace our v in this v squared with omega r, let's see what we get. We get centripetal acceleration equals omega r, all of that squared because v is squared, and then we divide that by r. Now I want to expand this out. So centripetal acceleration equals omega squared r squared divided by r. And notice that I have r squared on top, I have r in the denominator. So one of those r's will divide out, and now we have centripetal acceleration equals omega squared times r. So if you're given centripetal acceleration, or you want to calculate centripetal acceleration, if you're given angular speed instead of linear speed, you can actually still calculate centripetal acceleration without having to say, oh, let's convert this to linear velocity before I plug it into this formula. Instead, you can go straight to this formula right here and just say centripetal acceleration equals omega squared times r. Okay, class, that's what I want to introduce to you today, and tomorrow we're going to work through some examples and make sure that we have a really solid understanding of linear velocity, angular velocity. That's a really important concept to understand the difference between. Alright, well, look forward to seeing you tomorrow, and have a good evening. Bye.